Okay, I think we'll get started. Good afternoon, everyone. My name is Dave Ludgate, and on behalf of the Water Environment Society of Engineers Ireland, I'm delighted to welcome you to today's webinar on micropollutants. Today's presentation will be by Fabio Bacci of Glanua, and we aim to be finished by 2 p.m. Following Fabio's presentation, there'll be time for Q&A sessions, so please use the Q&A function to ask any questions you may have for Fabio. So just to introduce, Fabio is a chartered water and environmental manager specializing in emerging pollutants. Fabio was awarded a PhD by UCC in 2017 and is currently an MBA student at UL. In his capacity as innovation manager of the Glanua Group, Fabio works on business development for innovation, adhering to the pragmatic principle that progress must be governed by an equilibrium between environmental stewardship and the essential advancements necessary to ensure societal well-being. Fabio and I first crossed paths at the British Water Micropollutants Focus Group, which Fabio actually founded in 2020 and has acted as chair and convener of the group up until July 2023. Fabio's ambition is to continue cultivating an ethic of contribution to make emerging water quality challenges a collective mission of the water industry. So with that, I'll hand you over to Fabio.
Thank you, Dave, for the kind introduction, and good afternoon, everyone. First, I'd like to start by really thanking Engineers Ireland and the Water and Environment Society for the opportunity to present on this topic, which is obviously close to my area of expertise and my interest. I don't think I have anything else to add to what they've already mentioned about myself and the fact that I lead innovation within the Glanua Group. We are an engineering contractor working in water and wastewater design, building and operation. So the topic of micropollutants is also very relevant to my current role. So I'll dive straight into the presentation. The presentation will cover a number of topics, and the content of the talk will start with the classes of micropollutants that I will cover, and basically they form the full scope of micropollutants that we know. Starting with biocides, many of us are already well familiar with herbicides and pesticides and the issues that they do cause to the environment. Then I'll move on to surfactants and personal care products. Then the infamous per and polyfluorinated alkyl substances and the problems that they are causing, or the challenges they are posing to the water industry. Veterinary drugs will not be covered in any details, but they essentially are very similar to pharmaceuticals used for human consumption. So the two topics, or the two micropollutants, are similar in the type of impact that they cause on the environment. Then I will look into briefly touching on sources and pathways in the environment, the current or the latest EU regulation and the latest frameworks that are effectively generating an industry, a niche industry, if you like, but nonetheless there will be an industry generated by this legislation. Then I look at treatment technologies very briefly, the most emerging or the primary technologies used for micropollutants, particularly PFAS. And then I'll touch on why pharmaceuticals have to be treated differently from other classes of micropollutants. So I just to put everything into the right context, or to frame everything correctly, I want to start with just a brief glossary. So what I mean, or what the presentation refers to as micropollutants, are organic chemicals They are found in trace levels of parts per billion or parts per trillion in the environment, or micrograms to nanograms per liter, and they have the potential to cause a negative impact on the environment and pose a hazard to human health. They are somewhat, not all of them at the same rate, but they are prone to bioaccumulation, meaning they concentrate in organisms, they biomagnify along the food chain, or they have the potential to biomagnify. Some of them have endocrine disrupting potentials, which means that they basically mess with the endocrine functions of organisms. They might show negative removal efficiency, meaning that they are detected in higher concentrations in the effluent of wastewater treatment plants relative to the concentrations in the influent. They are POPs, or many of them are POPs, or persistent organic pollutants. They are prone to bioaccumulation, biomagnification, and long-range dispersion, either in the aquatic environment, on some of them through atmospheric transport and deposition. And then many of them show these particular characteristics. They are pseudo-persistent, meaning that they might not be persistent in the environment, and they might break down relatively quickly within days or weeks through natural breakdown processes, but nonetheless, because we continuously emit them, they become pseudo-persistent within the receiving water body. So there might be a plume from a point discharge where emission causes this persistence to be pseudo-persistent or relatively consistent. So moving to biocides, the pesticides that are of most concern to Ireland are MCPA, 2,4-D, and glyphosate for the treatment of rush, I think it is. The main sources are agricultural practices. They get a lot of the blame, although there is a lot of work done from the agricultural community, and they are very responsive to stewardship, but nonetheless, unfortunately, a lot of the blame ends up falling on the agricultural community. Spot application is also very important. For example, glyphosate is applied through spot application, but nonetheless, any type of application to groundwater through runoff will seep into groundwater courses or groundwater bodies and discharge into stormwater. So it will eventually reach either a wastewater treatment plant or potentially be abstracted for water treatment for water consumption. The environmental concentration is very prone to seasonality, obviously. And what's important to bear in mind from the point of view of operating or designing plants is the fact that many of these chemicals are in the market, but the trend of the distribution of the chemical in the market might basically go up and down. There is a particular trend. For example, in this graph, I'm showing the market displacement of simazine in the Czech Republic during the beginning of the century, 2002 to 2006. But if a monitoring campaign were to check for simazine between 2003 and 2005, it would show that the concentration of simazine in aquatic bodies or ambient water is quite low, but that's simply because there might be shortage in the market and atrazine is effectively displacing that simazine out to the market, or simazine might be phased out of the market, etc. The cause is not relevant. What's important to understand is that oftentimes we are so dependent on micropollutants from a societal point of view that if one is declining, or the trend shows that one is declining, or the utilization, the detection in the environment is declining, more often than not is because another one is increasing and is replacing or displacing that particular micropollutant. We see these similar effect later on for pharmaceuticals. Moving on to surfactants and personal care products, these are detergents that we are all very familiar with. All of these products are present in households. They are very common. The primary issue with many of these surfactants and personal care products are that they show endocrine disrupting characteristics. So they can have an impact on organisms. Triclosan is by far the most commonly found in soaps and detergents, or human detergents. Nonylphenol is the only regulated one. We'll see later the regulation, but is the most commonly found in detergents. And then there are the parabens. These are preservatives for personal care products. They have mild ED characteristics, but they do react with chlorine. So because we emit them constantly through wastewater or grey water in some cases for detergents, and they do react with chlorine, we have a similar problem with what we have with the humic and fulvic acid or organics in water, the generation of disinfection byproducts. So they do are a cause of concern. The primary pathway is basically effluent discharge and waste disposal. Or in this case, I wouldn't call it inappropriate waste disposal because there is no collection system as we might have for pharmaceuticals. So once a product, particularly a personal care product, is out of date, disposing the product in a correct way is, it's not there. There's only municipal solid waste disposal systems that are available for these. And all of these are prone to pseudo persistence, so that they are discharged continuously in the environment. And then we have PFAS. This is the biggest challenge that the water industry is facing at the moment. When I started following the discussion within the water industry on PFAS and micropollutants, which is 2018, 2019, not that long ago, generally during the discussion, the figure of 4 to 5,000 known PFAS would come up at some point or another. Because there has been so much research, so much attention on PFAS over the last 5 years, methods of detection have improved, the limit of detections have decreased, etc. Now we know that there are between 13 and the figure of 16,000 PFAS compounds available or present on the market and in the environment. So because we look for them, we simply detect more of them. But they are primarily associated with the use of AFFF or aqueous film forming foams, primarily used in airports and military sites where a lot of these foams would be used for fire control. But firefighting foams are not the only source. They were used extensively in coating textile, for example, carpets or other textile products for households. And many of us do remember the trade name Scotchgard by 3M. Scotchgard were essentially PFAS used to coat textile and make the textile products more resistant, or less likely to stain, more hydrophobic, etc. So they have a lot of characteristics, but textile, cotton, and we are nowadays, if we buy a Patagonia piece of, Patagonia is not the only brand, but a Patagonia piece of outwear apparel, it's likely to say PFAS free, because PFAS is also found in a lot of outdoor equipment because of the hydrophobic characteristics. They are all long chain, long carbon chains. So the molecules are basically surfactants. They are long chains, carbon chains that degrade into the environment into shorter molecules that are more essentially always more toxic. So the shorter the molecule, the higher the toxicity. They are extremely persistent, and that's the challenge to the water industry. They are very persistent. They bioaccumulate, biomagnify. They are very recalcitrant to most traditional or conventional wastewater treatment methods or techniques. We see some of them that are very effective in a minute, and we do have a way to remove them. But what's important here is that they transfer atmospherically across the globe. So once in the atmosphere, they have the tendency to transfer over a very long spaces, and in fact are found in Antarctica, in organisms that would never come to any contact with textile coating or aqueous film forming foams. So they do disperse a lot. And then there is another source that is unfortunately not discussed as much as I think it should. And this is not speculative. This is, there are peer-reviewed papers that discuss these. PFAS are very strong binding, or they're very thermally resistant binders that are used in munition. And as munition detonates, it's logical to assume that they are either penetrate very deep into soil or disperse into the atmosphere and eventually reach these global atmospheric transfer. They've been heavily regulated by a really nice piece of legislation, the Stockholm Convention. The convention is a multilateral agreement between 152 parties, and as of today, I think, unless I didn't check the last few months, but it had 184 signatories. In 2004, it became binding for the parties. It was 9 years after the convention was formed. It was initially focusing on the 12 legacy POPs, the persistent organic pollutants, and many of us would be familiar from the beginning of the century, but the list has increased significantly, and now it includes a total of 18 new substances, mostly pesticides and fire retardants, really because of these, because of PFAS, and they're now listed in Annex B and the PFOI in Annex A. There is a lot, I can't go into details with some of the legislations. It would take an entire lecture just for these, but this is a starting point if any of you have interest in developing further knowledge of this. PFAS are, like many of the other micropollutants, are tackled in wastewater as well as water in using two trains or two technologies. First, well, this is specifically to PFAS. PFAS are first separated and concentrated and then destroyed. The other micropollutants, pharmaceuticals, pesticides, surfactants, etc., in the personal care products generally can be addressed using only separation and concentration, or separation techniques only. PFAS also requires the second train, which is destruction. And we look at these, some of the emerging and the well-known technologies for these two methods. So absorption is very well known. Granular activated carbon is by far the most well-known, accepted by the industry, recognized to work. The industry is very familiar with it. The industry is very familiar with operating plants that have a GAC filtration. So it's recognized and is accepted by the industry, and in fact is the technology that the industry, at least within our European region, is looking at for separation of PFAS in the short term. It's somewhat, there are some issues like short chain molecules are likely to break through, but nonetheless, GAC is a really good technology still. Ion exchange resins are also very good, slightly more expensive. They might have some issues with indiscriminate absorption of other organics, but they are also very effective in separating PFAS from a source water. Novel polymeric adsorbents, some of them are specifically designed with affinities for particular PFAS, whether they are ions, Zwitter ions, but they can be tailored for specific molecules, but the cost increases significantly. So CapEx and OpEx from the point of view of the industry will potentially make some of these technologies, separation technologies, not commercially viable. Physical separation, membrane separation, nanofiltration, and ORO are very well known, very well recognized as good technologies by the industry. Membranes come in submersibles, cross flow. There are so many suppliers that they're really, they are, all of these technologies are effective. And some are more emerging, electrocoagulation using immersed anodes and cathodes plates, using sacrificial materials, but they're all very effective. There is one issue though with PFAS, is that separation and concentration techniques make the product safer, being wastewater or before, prior to discharging it, or water for drinking water, disinfection, flocculation, post absorption, etc. Or but the biggest issue here is that any of these technologies generate a centrate that is full of, or is laden with the residual PFAS, very high concentrations of PFAS that have to be destroyed. So it does generate a byproduct that then leads to the second train of technologies, which is degradation and destruction. The most recognized as effective are thermal treatment, incineration, and pyrolysis. They are selected in some jurisdictions, other jurisdictions globally stay away from thermal treatments, but in Europe, 3 or 4 main jurisdictions have decided to go down the route of using incineration. Pyrolysis was very prominent in the US for a while. A lot of testing went on, particularly because of the generation of biochar, which can lock carbon, so it has an additional benefit. But thermal treatment is questionable. Advanced oxidation processes, sonochemical is very effective, but is very expensive, and it makes it commercially difficult to justify from a CapEx and OpEx point of view. Electrochemical oxidation is perhaps the most promising, and because of the new legislation in the US, a lot of the electrochemical oxidation providers find themselves at capacity at the moment, and this is a very recent development from the Biden administration. I think it's the bipartisan, I can't remember the legislation that was passed very recently, but this is likely to cause an impact on the supply chain of the most favorable technologies, or the one that have a commercial viability, such as electrochemical. And then there are some emerging thermal oxidation treatments. One of them is supercritical water oxidation that is getting a lot of attention because it's a self-sufficient. Once it reaches a steady state, it becomes a self-sufficient technology. I'm not going to go into details with the technology. The names are there. There's a lot of information on the techniques, and it can be researched later. But this is a sample of the most commonly used or intended to be used by utilities and some emerging technologies. As I said, all the separation technologies apply to all the micropollutants, whereas the degradation and destruction are very much for PFAS only. And now we'll move to pharmaceuticals, the last group of micropollutants that I'll discuss. And this is where most of my research was exclusively on pharmaceuticals. So that is where I have more first-hand knowledge. So there are over 3,000 approved pharmaceuticals present in the global market. And because of our lifestyle and population aging, to mention two of the factors, two factors only, consumption is increasing significantly. So we rely heavily on pharmaceuticals. The main pathway of excretion is basically utilization, consumption, metabolism, and excretion. A minor percentage is attributed, it can be attributed to inappropriate disposal of spent or out-of-date pharmaceuticals through flushing down in the toilet, or perhaps disposing it through solid waste. But nonetheless, the excretion or the ingestion and excretion pathway is by far the most important. And also, municipal wastewater is the biggest contributor of pharmaceuticals in the environment. Pharmaceuticals from healthcare facilities such as hospitals are treated somewhat within the wastewater treatment plant of the facilities themselves. But there's plenty of documentation, peer-reviewed documentation, that demonstrates that municipal wastewater is by far the biggest contributor. Conventional wastewater treatment is not designed to treat these compounds, and they tend to make their way through it to treated effluent, and because we do consume so much of these compounds, they are pseudo persistent in the receiving environment. But they're also designed to have specific biological effect, cardiovascular, on the nervous system, on the cardiovascular system, on musculoskeletal, and they are intended to have an impact on organisms. So basically, discharging them in the environment is exposing the environment to something that is designed to have an impact on it. And also, drug interaction is very important. We are very familiar with drug interaction when we go to a GP and we require a prescription. The first question we are asked is whether we are already on some medication, because we know that if we are on a blood thinning medication, we can't take other medications that might interact with the one that we are already on. But nonetheless, we discharge all of these medications in the environment as a cocktail. So the environment is exposed to a multitude of medications. So the regulatory process from an environment point of view, the Priority Substances Directive included non-steroidal anti-inflammatory drugs or diclofenac earlier on in 2013, and started increasing the list by adding estrogens because of the ED characteristics. But then we see in year 2015, 2018, and 2020 a significant addition of antibiotics because of the antimicrobial resistance issue or challenge that we are facing, not just the water industry, but as you know, humankind, because they are, it's likely to generate a super bug that is going to cause the next potentially significant health issue globally. In 2019, the European Union strategic approach on pharmaceuticals in the environment was a very important piece of work that raised awareness, but also encouraged innovation and promoting the circular economy. I can't justify that particular phrase, but encouraging innovation will come up in one of the slides later. And this is quite important because of the quaternary treatment required. And I'll get back to that in 2 slides. Recent regulation updates in drinking water came in 2020, at the end of 2020, and 2 micropollutants were added. Nonylphenol, we mentioned it earlier, is the only one of the surfactants that is actually regulated and is found in detergents, and the 17-beta estradiol, again, because of endocrine disrupting properties. And then the implementation decision of 2022 established a monitoring system of 8 additional pharmaceuticals going forward, obviously, to inform future legislation. So there's one SSRI, venlafaxine, an antidepressant, metformin, an antidiabetic, but most of the rest are, again, antibiotics or antibacterials because of AMR or antimicrobial resistance issues and challenges that we are facing. And then wastewater. This is the most important piece of legislation from a market or an industry point of view. In October 22, the Council directive, the Urban Wastewater Council directive was recasted, and it included a timeline whereby 2025, the setting up the extended producer responsibility scheme. This is an absolutely novel piece of legislation where the polluter pays principle, which is Article 2912 of the Treaty on the Functioning of the European Union, has been basically implemented for the first time, and I'll get back to that. But by 2030, plants that have a population equivalent greater than 100,000 PE, and by 2035, facilities greater will have to be equipped with, and by 2040, at the end, equipped with quaternary treatment, which is discussed in Article 8 of the legislation. This entails basically a polishing filter after tertiary treatment, which is it's not there at the moment in any of the plants in Ireland or the rest of Europe, for that matter. Perhaps Switzerland is looking to implement in some of these. So these will generate a market, and this is where the innovation is required in quaternary treatment that is effectively commercially viable. But the important thing from an environmental point of view is the application of the extended producer responsibility. As I said, this is the first time that the polluter pays principle has been implemented. But the interesting part is that Article 9 shifts the responsibility on the pharmaceutical industry, not the water industry anymore. So the pharmaceutical industry will be the pharmaceutical industry will have to pay for 80% of the quaternary treatment costs, I presume CapEx and OpEx, and the utility running the plant will incur only the other 20% of the cost. So this is, from an environmental legislation point of view, it's a really noble change that the Commission decided to embark on. How this is going to pan out and be implemented with the pharma industry, it's a guess. I don't have any updates on that, and there is a lot of speculation on how these can be implemented, but this is certainly a very important piece of legislation. And now let me just put this into a brief context. I'm almost there. On the consumption of pharmaceuticals in Ireland. My research was done in 2009 to 2012, so this is a little bit dated. So between 2009 and 2012, the amount of prescriptions, not over-the-counter prescriptions, but prescriptions requiring or dispensed item requiring a prescription increased from 64.5 million units in 2009 to 72 plus million units or products in 2012. Products doesn't mean a dose, it means a monthly supply, a weekly supply, or a course of antibiotics. This increases, it increased by 12% in a 4-year period. Population size only increased by 1% over the same period. So our reliance on pharmaceuticals in Ireland is skyrocketing, but this is not unique to Ireland. This is across the globe. And in Ireland, the Irish market is about 1,300 different pharmaceuticals available on prescription. The figure inflates with over-the-counter products. Yesterday, I thought, maybe this is a little bit dated, 2012. Maybe I'm going to be asked the question, what about today? So yesterday, I looked at the annual reports by the PCRS, readily available on the internet. And to give you an update, for the period of 2009 to 2022, the increase in primary care reimbursement claims, which is the number of products dispensed, increased by 43% over the 13-year period. And now we are at 92.4 million products prescribed per annum in 2022. So by now, we're probably close to 100. And now, returning to the utilization, this is using data from utilization from consumption of pharmaceuticals, we can really determine how much can be potentially found in the influent of a wastewater treatment plant. And this was my research, and it is possible. There are a lot of statistical models that can determine that. But I want to draw attention to some of the emerging contaminants, emerging pharmaceuticals, in this case 4 that have been introduced in the market in 2008. The y-axis shows the kilogram dispensed per month in Ireland, and the x-axis is obviously the time. So these are time series that show a particular increase. Let's take the first one, pioglitazone, on the upper left tile. You can see a significant increase there, a spike in 2010, 2011. That's simply because pioglitazone replaced another anti-diabetic, rosiglitazone, that was phased out of the market because of a health warning issued by the European Medical Agency. So from an operation point of view, we can deduct a lot of what is going to be in the influent by following other trends, by following the consumption of or the market availability of pesticides, herbicides, pharmaceuticals. PFAS is somewhat different, but for some of these, we have control over what we know. Other ones are increasing for different reasons. This one, mercaptopurine, it's an anti-neoplastic, an anti-cancer drug, very potent, very toxic, and as you can see, 2008 introduction on the market, 2009 increase exponentially, although the quantity is limited. But the reason I draw attention to anti-neoplastics is because I think it's after the financial crash in 2007, 2008, a lot more cancer patients are treated as outpatients. So they are administered anti-neoplastic drugs, but they do not excrete them in a hospital environment anymore. But these anti-neoplastics are excreted 3, 4, 5 days after consumption or administration in wastewater or septic tanks in rural areas. So it's really important to address some of these issues because some of these are very potent. Going back to the antimicrobial resistance for research in particular, again, we see the seasonality aspect in this case for antibiotics. So from an operation point of view, should we be aware of the amount of antibiotics we are likely to receive in a wastewater treatment plant at any given time? Potentially, yes. However, a sub-series divided by month shows that here we have an inverted seasonality. Some antibiotics are dispensed more in winter months and less in summer months, and other have the inverse trend. So from an AMR point of view, which is very relevant to the industry, these are very valuable insights. And again, this is population aging. On the right-hand side of the graphs, we can see the consumption, and on the left side of the two graphs, the population divided by age segment. You can see that from 55 to 59 upwards, the increase of bisoprolol is skyrocketed again. So population aging is likely to have a significant impact on the amount of pharmaceuticals reaching wastewater treatment plants. And I want to finish with this particular graph, which is the population of which is using demographic to demonstrate the survival of the population of Ireland. These are the mortality rate for 1967 to 71, a 4-year period. If I project these to by 40 years, we can see that a lot more people survived to age 75 and over. The reason being that survival rate has increased so much because of lifestyle improvements, certainly, but medical progress, earlier diagnosis, increased prescribing of preventive medication. Statins are typical, and advancement in prognosis and palliative care, all leading to increased consumption of pharmaceuticals. And these are the projections of population aging for Ireland. So by 2041, it's very likely that we'll have a lot more people on in a pensionable age than we had 30 years ago. So again, these will lead to an increase of pharmaceutical consumption. So the main points that I want to drive home is that many of these pharmaceuticals are pseudo-persistent. They end up in the environment continuously discharged, and this is very important for antimicrobial research and for AMR problems. The biological effect of pharmaceuticals is what they intend to cause. They are designed to have a specific biological effect. So the exposure or the long-term or chronic exposure of organisms to trace doses of pharmaceuticals is unknown at the moment, particularly when we include the drug-to-drug interaction or the exposure, chronic exposure to trace levels, albeit of cocktails of pharmaceuticals. And then the human health progress, sorry, there's a typo, I'm missing the end there. Because of the increase in survival rates and assisting population aging, there is an ethical and a moral issue. We can't phase out pharmaceuticals. So the only available alternative is end of pipe. And finally, insights from a market point of view. PFAS are the main challenge faced by the industry and the one that will likely drive innovation in quaternary treatment. And phasing out PFAS is already there. I mean, there are a number of lawsuits with DuPont, 3M in the US, but nonetheless, the concentration that we have there in the environment will remain there for decades. Biosolids as bioresources is a very important um, topic of conversation at the moment. However, the fact that PFAS are so persistent and likely to end up in biosolids, this is likely going to be a spanner in the works for bioresources. Pharmaceutical products, phasing them out is impossible. Ethical and moral issues and moral imperatives don't, we can't. So the only available alternative is end of pipe treatment. And then the market response is unfortunately still due to command and control. Unless there is coercion from the legislators, the, you know, there is no uptake of innovation, voluntary innovation. So the economy will develop around legislation. And I want to leave you with this very powerful image that I use a lot, just as a reminder that the likelihood is that those that are impacted are invariably the most vulnerable. So I think I start always by bearing that in mind, is that, those that are more vulnerable are the ones that will end up being at the end of the fight. And I thank you all for your attention. I hope I didn't go over time, and thank you to all, and I'm ready to take questions.